This video is going to be about vertically accelerating objects. The most common type of problem we're going to see is an elevator problem. So a guy or a girl standing on a scale in an elevator, what does the scale read? So the scale reading that they're looking for is really just another name for the normal force, which is occasionally referred to as apparent weight, meaning how heavy do you feel? Not how heavy are you, because the force of gravity is always going to act on you the same way until you get to like the moon, but how heavy do you feel? So if you've ever been on the Sasquatch ride or a very fast elevator, you know that sometimes you feel heavier and sometimes you feel lighter, sometimes you don't feel any different at all. Okay, so let's say in our first example, we are accelerating upwards. We'll just say we're accelerating upwards. Okay. We'll not put any numbers on it. Got to keep it similar to the test. So we're accelerating upwards. So this means that we have a positive acceleration. Okay. So this could happen in one of two ways. We could either be moving up and speeding up. Okay. Or the other less common way is moving down but slowing down. So whenever you're slowing down, your direction of acceleration is opposite your direction of motion. So if we're moving down with a speed v but decreasing speed, our acceleration has to be pointing upwards. Whereas if we're speeding up, acceleration and velocity have the same direction. Okay, so we have a positive acceleration. Awesome. So as this guy stands on his scale and he is accelerating upwards, there are only two forces acting on him, Fg and the normal force from the scale. Okay. So if we are accelerating upwards, then our net force equation looks like ma. I remember that this is really our net force. Okay. So if our acceleration is directed upwards, then our net force must be directed upwards as well. Okay. Acceleration and net force share direction. Okay. So thinking about this logically, if we have an upward net force, okay, that means necessarily that the normal force needs to be bigger than gravity. Okay. So whenever your normal force is bigger than gravity, you are going to feel heavier, which makes sense because the elevator has to work extra hard to accelerate you upwards, so it has to apply a larger normal force on you than a force of gravity. So our equation for this would just look like normal force minus Fg equals ma, and to get our normal force, we would end up doing ma plus mg. Okay. And we see that our normal force is in fact going to be greater than our force of gravity because we have this additional ma term in it. Okay. So now let's talk about if we are accelerating downwards. Again, we're still talking about this guy on an elevator on a scale. Okay. So if we are accelerating downwards, this would be considered a negative acceleration if we're considering down to be negative. So this can happen in two ways. Okay, we can either be moving down and speeding up. Remember, anytime we are speeding up, velocity and acceleration have the same direction, or we can be moving up but slowing down. So whenever we're slowing down, velocity and acceleration are in opposite directions. Our free body diagram looks exactly the same. Only two forces are Fg and Fn. And our net force equation is going to look like this. Okay. One thing to pay attention to is that we need to plug this acceleration in as a negative. So this is really going to look like negative ma. Or I should have written as mass times a negative a. So this means that our net force is negative or downward. So that means our downward force has to be larger than our upward force. So Fg is going to be greater than Fn, or written like I did before, Fn is less than Fg. So this is when we might feel lighter. Okay. So our net force equation looks like Fn minus Fg is a negative ma. Again, that negative is there because we have a negative acceleration. So normal force is Fg minus ma in this case, which again, that goes with the Fn less than Fg. The last way we could move in this elevator is at a constant velocity. Now, it doesn't matter whether you are moving up or down, okay? Because whenever you are moving at a constant velocity, your acceleration is 0. So remember, constant velocity is a very highly underlinable word or phrase. So we have normal force, force of gravity, okay? We have our net force equation. Instead of equaling ma, we're going to equal 0 this time. So normal force minus Fg is 0. So normal force equals Fg. And this is when you would feel normal. You don't feel heavier. You don't feel lighter. You just feel the same. Again, you could be moving at a constant velocity upwards, constant velocity downwards. This even works if we are at rest. You feel the same. Okay, that's because our acceleration is 0. And in order for that to be true, the normal force and the force of gravity need to be equal.